Okay, so today we're talking about graphs of the tangent, cotangent, cosecant, and secant functions. You may want to refer to your unit circle packet, which I gave you before. The staple that has your unit circle here. It has your trig identities chart. Those are available. And then this is the page, and the back of this could be pretty useful. This has your sine and cosine information, like your amplitude, your maximums, and so forth, your x-intercepts, your minimums, whether it's odd and even. And then on the back of that page, it's called Other Circular Functions, and that's what we're doing today. It's on tangent, which looks like this, but this is just one period worth. Cotangent, which looks like that. We're going to talk a lot about the differences, but tangent goes through the origin, and cotan has an asymptote at the origin. So in that respect, they're opposites. We'll talk a lot about that later. Both functions are odd. And then here's the thing about the secant and the cosecant. So since the secant is a reciprocal of cosine, that's why the top part is going to touch. Let me show you what I mean. Okay, well this example is about sine and cosecant that I already have graphed. So the high part of sine is the same as the low part of cosecant. And the low part of sine is like the high part of cosecant. So that's why it works that way. And then I'll do the others. This will be secant. And then this has to be cosine. So that's one way to tell which ones go together. The C and the S go together. Okay, so again, you may want to refer to this chart, and it tells you both of these are even functions. This part of the handout isn't quite as useful as all the other parts. Basically, on this one, we're talking about the cosine graph. And so you look at your x value going from 1 to 0. And so because of that, that's why on the corresponding graph, it starts at 1 and then comes down. And then it just continues. I'm not going to read through this part. You can on your own time. But it basically explains how this is related to this. And again, on the sine part, sine relates to y. So your y is going from 0 to 1. And so that's why it's increasing. And then here it's going from 1 to 0, so it's decreasing again. And so that's how your graph grows. Okay, all that's a little bit extra information for how the unit circle is related, but it is. Okay, so now let's actually work through our notes. We have functions of the form a tan wx plus b. Just as a reminder, the a represents the amplitude. The w, it's based on how often or how frequent the graph repeats, and so we can call that frequency, and it affects the period. Just like on sine and cosine, it affects the period. And then this one would be the vertical shift. Okay, so these are your functions. We're continuing our study of trig graphs. I suppose we could put over here cosecant is 1 over sine, and secant is 1 over cosine. We put that other places, but if you want to put that here also, you can. So two of the functions in this section have ranges that are all real numbers instead of domain like sine and cosine. And then two of them are reciprocal functions of sine and cosine. Applications and word problems related to this are carrying a ladder around a tight corner in a hallway and a rotating beacon. Okay, so again, you can refer to that handout, but we're basically going to have the same blanks and fill them out here. The domain for tangent is the set of all real numbers except odd multiples of pi halves. The range is the set of all real numbers. So again, we're talking about tangents, so the tangent graph looks like this. It's repeating and it's increasing, and it goes through the origin. Alright, so we have the range as the set of all real numbers. The tangent function is an odd function since it's symmetric to the origin. The tangent is periodic with period pi. So remember, tangent and cotangent are the ones that are pi. I'm going to move back up to the top and show you something. You may want to put your extra formulas like your period is your normal period divided by W, your W is your normal period divided by T. But for tan and cotan, that would have to be pi over T. But for cosecant and secant, it would be 2 pi over T. So you see the difference that on tan and cotan you'd put pi on top, and on cosecant and secant you put 2 pi on top.
Wait, for secant and cosecant, what?
2 pi on top of T. Because remember, if sine and cosine had normal period 2 pi, then so did cosecant and secant. Yeah, for the parent function. All right, good. So now back to here. The tangent is periodic with period pi. Oh, do you don't need that again?
No, it's good.
Okay. And the x-intercepts are listed. There are many. It's basically, think of it as plus and minus 2 pi k. That's actually incorrect. That should be plus or minus pi k. I'm going to do this over. Plus or minus pi k. Because it's a 0, 1 pi, 2 pi, 3 pi, as well as negatives. So this is plus or minus pi k. And then the y-intercept is 0. There's only one y-intercept, and it's 0 because it goes through the origin, 0, 0. That's for tangent, yeah. And then your vertical asymptotes occur here. So those represent plus and minus and odd pi over 2 times k. So this one would be like 2k minus 1 over 2 times pi. Because if you substitute in 0 there, you get negative pi halves, which is this one. If you put a 1 in there, you get 2 times 1 is 2, 2 minus 1 is 1. So you have 1/2 pi, which is the same as pi halves. And looks like if you plugged in a negative 1 for a change, you get negative 2 minus 1, which is negative 3. So that was if k equal negative 1, then you go 2 times negative 1 minus 1 over 2 times pi. So that's negative 2 minus 1 over 2, which is negative 3 pi over 2. So usually we just start with k equals 0, 1, and 2, but there are extras because they didn't use the same interval that we did earlier. But it should work for all values of k. Every single k. Alright, number 2. While the tangent graph goes through the origin and it's increasing past the origin, cotan has an asymptote at the y-axis. The asymptotes of cotangent are where the tangent has x-intercepts. So in that respect, they're opposites. The x-intercepts of cotangent are where tangent has asymptotes. Don't forget the p in asymptotes. It's silent, but it's fine. I'm not going to count off for spelling. Also, the normal parent graphs go in different directions. Tangent is increasing and cotan is decreasing. So what we mean by a parent function in this case is tan x, not negative tan x, 5 tan x, tan 5x, or tan x plus 5, just as examples using 5. So the parent would be plain and boring. So the tan is increasing and it goes through the origin. It would look like that, and then another one. So that's tan. And then cotan would not go through the origin and it'd be decreasing. Any questions about that? Okay. Number 3, the cosecant and secant functions are sometimes referred to as reciprocal functions. And they're graphed by making use of the reciprocal identities. Again, refer to your notes. Cosecant's 1 over sine x and secant's 1 over cosine x. And number 4 just shows you how the minimums of cosecant is related to the maximums of sine. So remember, the low part of one was the high part of the other, and so forth. So remember, if you did sine x, there it is, and cosecant x would be touching it. Cosecant x. So this range would look really weird if you had to write it. It'd be y greater than or equal to 1, and also y less than or equal to negative 1. The other notation? Okay. That's a good question. Let me write this out for a second. Cosecant range would be y greater than or equal to 1 and y less than or equal to negative 1. So in the other notation, it would look like from negative infinity to negative 1 bracket, because it actually does touch there, union bracket 1 comma infinity. Because if it's greater than or equal to, it's called unbounded. Yeah. Unbounded. Okay, so this one was minimums of cosecant are the maximums of sine, and then the maximums of cosecant are the minimums of sine. And then the next one, the local minimums of secant x occur at the local maximums of cosine, and the local maximums of secant occur at the local minimums of cosine. And then here's your problem numbers you can start writing, and I'll hand out your trig graph paper now. Alright, so there's your header, and the first ones are your vocab questions. And number 3, basically talking about properties of tangent. So tangent is symmetric to the origin. It has vertical asymptotes at x equal plus or minus pi halves, and odd multiples of pi halves. So tangent is symmetric to the origin. It has vertical asymptotes at plus and minus pi halves and odd multiples, like 3 pi halves, etc. Number 4, this one is asking about secant. So this one is symmetric to the y-axis. And your vertical asymptote is basically the same as tangent. So again, that's how those two are related. Any questions? Okay. Number 5, it says to graph secant, first graph cosine. That's if you're doing it by hand, not on the calculator. To graph secant by hand, first graph cosine. And for the calculator, just make sure you're in radian mode. To graph secant by hand, first graph cosine, and if you're just using the calculator, make sure you're using radian mode. To graph secant by hand, first graph cosine, calculator would have to be in radian mode. Okay, number 6, this is a true-false question, and it says these 4 functions, and we mean tan, cotan, secant, and cosecant, have infinitely many vertical asymptotes. And that's true, because you have lots of places where it approaches either positive or negative infinity. Now compare that to sine and cosine, which said infinitely many x-intercepts. So on number 6, it is true, and for these 4 functions you have infinitely many vertical asymptotes. On sine and cosine you have infinitely many x-intercepts. I'm not going to count off for spelling, but infinite doesn't have an A in it. I've seen it before. INFINITELY. You're welcome. No problem. All right, number 7. This one is asking for the y-intercept of tan. Since it goes through the origin, the answer would be 0. It's not asking for an ordered pair on the Math Excel, so just put 0. Number 8, the y-intercept of cotan. That one doesn't exist. Does not exist. Or if you'd rather put D, N, E, that is a D, not a 1. D, N, E. You can do that. Due to a vertical asymptote at x equals 0. Okay, number 9. This one says the y-intercept of secant, and that'd be 1 since it's 0, 1, like cosine. So again, if it asks you to put it as an integer, then you put 1. Don't put the ordered pair. And number 10, if it asks you about the y-intercept of cosecant, CSC, that's going to be undefined. I guess we could have put the same thing for cotangent, undefined instead of does not exist. Just whichever way. Right. Yeah. Due to the vertical asymptote. At x equals 0. Okay, now I'm going to graph secant because we need that for our next question. Not yet. I'm just graphing on the calculator. Okay, so what I did was on the calculator I put sec x, and that's blue, and then I put 1 for that line. So the reason is because on number 11 it's asking for what interval on negative 2 pi less than or equal to x less than or equal to 2 pi does, okay, for what interval on negative 2 pi less than or equal to x less than or equal to 2 pi does secant x equal 1? Bless you. So what I did, you don't have to write this part, is I put f1 as secant x and I said f2 is 1. So right, it looks like it's the minimums. So this one we can tell is 0. This one, let's find the minimum. So we go to Analyze Graph, Minimum. It's asking the graph, so I have to choose the blue one. And it says the lower bound, to the higher. It says 6.28. Hopefully you recognize 6.28 as 2 pi. So, right, yeah, so it's going to be 0 and plus and minus 6.28 something. So that's really 0 plus and minus 2 pi. Not for this. They're going to want the exact answer. Good question. And again, if you'd rather use your table, you can. You can do Control-T to get to your table. Now at this point, with all these decimals, it doesn't make sense, but if you go up to 0, it's 1. So you can go to your table settings and start at 0 and then step by pi halves. Pi divided by 2. Or if you would rather just change it to ask, you can. But if you go by pi halves, you can see that it's pi halves is undefined, pi is -1. The 4.71 would be 3 pi halves, which is undefined, and 6.28, which is 2 pi, would be 1. And then the pattern just repeats. So then this would be 4 pi. Remember also, if you want to be very fancy, you can go to where this is, press Control-C to copy it, and then go to the calculate screen, and then do Control-V to paste it. Now, it's not going to convert it to something in terms of a square root or pi, but if I just put that there for reference, and then put 4 pi, Control-Enter, it shows me the same decimal. So it won't convert the square root for you, but you can double check things that way. You use Control-C and Control-V. Any questions? Okay. Alright, so we have 0 and plus and minus 2 pi. Okay, next we have number 12. This is asking about cosecant. Actually, the exact same question. Let's see, same question for cosecant x equal 1. Still going to use the same interval. So what we have to do is change the graph. So I'm going to current, getting rid of my table, and I'm changing secant to be cosecant. CSC x. Okay, so it did move slightly. If you blinked, you missed it. But we know, based on our paper also, which you can refer to, that, let's see, secant was over here like at 2 pi and at -2 pi. Well, that's off the page. At 0 and 2 pi. But on cosecant, it would be at pi halves and 3 pi halves. So I'm just going to use this page to show me that. If we change our table, we could have figured that out also, but let's just use our resources. So this would be plus and minus. Well, let me not do plus and minus. Let me say for cosecant, pi halves and 3 pi halves. Oh, pi halves would be where it's 1. 3 pi halves would be where it's -1. So let's see, we might have one more answer for this. From this dot right here, where it touches at 1, it's at pi halves. On your calculator, it would look like 1.57 something. Okay, let's check. Go to a minimum graph. So analyze minimum. I want to choose the blue graph and go from here to here. And that's where I see my 1.57. Let me drop that. And we also want the negative side. So let's go to minimum. Again, for this graph, between here and here. This one's negative 4.71 something. So that's negative 3 pi halves. So those are going to be your two answers. So pi halves and negative 3 pi halves. That's going to be our stopping point for the day. We can do the others the next time.